Okay, some sample problems for chapter 28. Here I have four very long current carrying wires. It tells me I can write the magnetic field due to these guys as being equal to mu naught I divided by 2 pi r. They're each carrying the same amount of current, and I'm told I know what this that this is a square and it's going to be 0.2 meters along its side. I'm asked to find the magnetic field there, and there. So let's start with the first one. So the first one is carrying 100 amps. I use the right hand rule to figure out the direction. I put my thumb into the page. That's where the X with the circle means, and I curl my fingers around it. So my fingers kind of come around here, and I have my magnetic field due to 1 in black. Number 2, I do the same thing. Put my fingers into the page, curl my fingers around it, and at the center it's going to point in that direction. For number 3, I'll do that in blue. Again, point my thumb into the page in the direction of the current, curl my fingers around. And lastly, for 4, you know the routine, fingers into the page, curls around. Since the current is equal and the distance is all equal to, it is all the same, magnetic field is going to be equal to 0 for this instance. Now let's look at this one. Here, this means my thumb comes out of the page and I curl my fingers around it. See that my magnetic field is going to be in that direction from 1. Number 2 is going to be into the page. So it's going to look like that, my magnetic field. Number 3, curl my fingers around. It's going to be in that direction right there. And lastly, number 4, thumb goes into the page, curl my fingers around, and we can see that my magnetic field is also going to be 0 in this instance right here. So last example, got 1, curl my fingers around, thumb coming out of the page. See the magnetic field is going to be in that direction. Number 2, thumb goes into the page, curl my fingers around, magnetic field is going to be in that direction. 3, into the page, and the magnetic field is going to be in that direction. And lastly, 4, thumb comes out of the page. Let's change my color here. Thumb comes out of the page, curls around into that direction right there. Now again, magnetic fields, our currents are all the same, radii are all the same, and you can kind of conceptually see that in the y direction things are going to cancel each other out, and I'm just going to kind of have some net magnetic field in this direction right here. So now we know the direction, let's figure out what the magnitude is. Really we can say that the magnetic field is going to be equal to the magnetic field from 1 plus the magnetic field from 2 plus the magnetic field from 3 plus the magnetic field from 4. And we can use symmetry to say that this is going to be a 45-degree angle, so it's going to be cosine of 45. So what this is going to be is this is just going to be 4 times mu naught I divided by 2 pi r cosine of 45. So that's going to be equal to 4 multiplied by mu naught, 4 pi times 10 to the minus 7th, multiplied by the current, which is 100 amps. Divide that guy by 2 pi, and then the radius. Radius is going to be that distance right there. So really the radius is going to be the square root of 0.1 squared plus 0.1 squared. And take r to be the square root of 0.02. You plug all that stuff in, we're going to come up with, oops, I forgot my cosine 45. And we're going to come up with around 4 times 10 to the negative 4th Tesla, with my direction being to the left. Okay, here we have 3 parallel wires. I'll call these guys wire number 1, wire number 2, and wire number 3. And there's currents going in them. They're all going to create magnetic fields, interact with the other current carrying wires. At the end of the day, we know that if the currents are flowing in the same direction, there's going to be an attractive force. So this is going to be the force on 1 due to 3. We know that these guys, are 1 and 2, are going in opposite directions, so there's going to be a repulsive force. There's going to be a force on 1 due to 2. Now let's take a look at wire number 2. It's going in the opposite direction of 1. So the force on 2 due to 1 is going to be repulsive. Similarly, there's going to be a force on 2 due to 3 that's going to be repulsive. And lastly, let's look at wire number 3. There's going to be a repulsive force due to force on 3 due to 2. And there's going to be an attractive force on 3 due to 1 because the wires are flowing in the same direction. I know that I can write the force per unit length to be equal to mu naught multiplied by the current multiplied by the other current. It's all the same, so I'm going to square that guy, divided by 2 pi r, r being the distance of separation. Distance of separation is going to be d, so we can immediately see for wire number 2 the forces are going to be equal and opposite, and so the net force is going to be equal to 0 for wire number 2. For wire number 1, what we can say is that the force per unit length is going to be equal to mu naught multiplied by the current squared divided by 2 pi, and this is just going to be 1 divided by d minus 1 divided by 2d, because the distance between 1 and 3 is 2 times the distance. So what we're left with is going to be mu naught I squared divided by 2 pi d, and the direction is going to be upwards, so that's going to be wire number 1. By symmetry, we can say that it's going to be the same for the bottom wire, mu naught I squared divided by 2 pi d, only it's going to be a net downwards. Why? Well, because it's closer to wire number 2 than wire number 1. Actually, scratch that. It's going to be 4 pi. I forgot to multiply my 2 right there. And lastly, let's take a quick look at calculating the magnitude and direction of the magnetic field at point P, so that point right there, for this half of a circle. Now the hint says, does the current in the long straight section produce any magnetic field? Well, let's take our thumb pointing along the direction of the current. Our finger is going to curl into the page right there. It's going to come popping back out of the page right over here, kind of the same, right over there, and we can see that there's no contribution from that section of the wire or this section of the wire. Now let's say, well, this is half of a circle. Let me just go ahead and complete that circle. I know how much magnetic field I'm going to have for a complete circle. The book already did that for me. That's going to be right there. This is simply half of the circle, so logic would dictate that the magnetic field is just going to be 1/2 of that of a complete circle. So I've just divided my complete circle by 2. As for the direction, use the right hand rule. The current's flowing in that direction, and it's going to be pointing down in towards the page.